Tree indexes. Let's start by recalling the API we had for accessing data in a heap file. We had two options for getting data out. The first was to use a record ID fetch, where we give the system a page ID and a slot ID, and it goes, finds that page, and figures out the offset on the page by slot, and returns us the tuple in the page. The alternative was to scan through all the records, starting from some page. So we could start, let's say, from the beginning and scan through all the tuples. But wouldn't it be nice if we could look things up by value? After all, we talked about having declarative languages like SQL. Couldn't we have a declarative access API that would return all tuples that satisfy some conditions? Well, we could with heap files, right? But it would probably be pretty slow. It reminds me of the way that we used to look at old catalogs. So the Sears Roebuck catalog, which was the most famous mail order catalog in the United States for over a century, had this great quote that said, "If you don't find it in the index, look very carefully through the entire catalog." Now, back in those times, there wasn't a lot of information for people to look through, so they enjoyed scanning the entire Sears Roebuck catalog. But we don't want to be doing that with our databases. It's pretty inefficient. And so we'll take an idea that goes back at least as far as the Sears Roebuck catalog, which is to build an index to allow us to find things quickly. And we will, in this case, avoid looking very carefully through the entire database. We've seen index type ideas before in our education, right? In our data structures courses, we saw indexes in RAM, things like search trees, binary trees, AVL trees, red-black trees, and so on, and also hash tables. These are data structures that allow us to do lookups without scanning through an entire data set. What we need here is some kind of persistent disk-based data structure, something that we can store in a disk and use with efficient I/O to go look up things in the index. So this is a data structure that's paginated. It's made up of disk pages, and we're going to need to lay it out intelligently on the disk so that each page that we fetch is used intelligently. So an index, what is it? Well, it's a data structure that enables fast lookup and modification of data entries by search key. So I want to unpack this definition, and for each of the highlighted terms, spend a little time thinking about what it means. We'll take them a little bit out of order. Let's start with lookup. So lookup in an index can vary depending on the kind of index that you build. The lookups can support different operations. The typical operation is equality. Find me all items in the index that match a particular value. But we might have lookups for things like ranges in one dimension. Find me all items in the index that are between x and y. Some indexes, particularly for geospatial data like maps, are for two-dimensional regions. Find me all items that are within a mile of where I am right now, or find me all items that are in a particular bounding box I drag on the map, right? And you can imagine other kinds of lookups for strings and for images and things like that. So there's been many data structures, many indexes invented for these different kinds of operations. And when someone presents you with an index, you should ask, well, what kind of operation is it designed to support? Now, we said that we look things up by search key. What did we mean by that? Well, in the relational model, what we're going to talk about is any subset of columns in the relation can be combined to form a search key. It doesn't need to be a unique lookup key. So, for example, we could have a search key that is first name in a table of people. Very likely that is not unique. Many people may match when you look up something like Joe. All right, but we could also look things up by a composite of multiple columns, like first name, comma, last name. And there we're looking for matches on both the columns. Okay, so the search key that we're looking on can be constructed out of any concatenation of values in the columns. Now, another term we had in this definition is a data entry, and this again varies by index. So the items that we store in the index depend on how we build the index. We'll assume for today that we're storing in our index pairs of the form key, K, comma, record ID. So for some key K, here's a record ID that matches that key. Record IDs, of course, are page, comma, slot. They're pointers to records in a heap file. So what this index would be storing is keys and heap file pointers. We can generalize this later and have different kinds of entries. Rather than record IDs, we could have entire records or something else maybe. But for our discussion today, we'll have key, comma, record ID. We talk about lookup. We also talk about modification. We want these data structures we're going to invent to be efficient not only for looking things up, but also for insertion and deletion of data from the database. Now, in some cases, we may have data that doesn't need to support insertion or deletion. It's static. But typically, for most of the cases we'll be interested in, we do want to be able to support modification of the database. Having said all that, I want to let you know that there are many index structures that have been invented over the years, and there are many that are in use in modern database systems. B+ trees are extremely common, but there are also hash indexes. There are R trees, they're a typical index for geospatial data. GIST is the generalized search tree, which can be used to build a whole different host of index data structures and is built into open source databases like Postgres. There are more.